Hello students, this is Janil Popat. We are discussing stress distribution. Let us continue with numericals. Problem number 3. It states that a concentrated load of 40 kN acts on a surface of soil. So, concentrated load of 40 is given. Determine the vertical stress increment at point directly below. So, we have to calculate vertical stress increment at point directly below the load. So we have to take radius as 0 and up to the depth of 10 meter with an increment of 1 meter and draw a plot. So it is quite easy to understand. Solution: we should write given data first. Q is equal to 40 kilonewton, R is to be taken as 0. Let us move to formula. So Boussinesq formula is already known. We should put it like that: sigma z is equal to IB into Q by Z square. See guys, whenever we are told to find out stress in increment of 1 meter or XYZ, whatever the meters are given, you have to use sigma z is equal to IB into Q by Z square formula because it will be easier to calculate. Now putting IB equation as 3 by 2 pi in bracket 1 upon 1 plus R by Z square and whole raised to 5 by 2. Now putting R value here, I will get IB is equal to 0.4775. So I got IB. Now in here I have Q is equal to 40, that is constant. I have got the IB value and I will put Z by increment. Let us check how. Putting Z1 is equal to 1 meter, I am getting gamma Z is equal to 19.1 kilonewton per meter square. Z2 is put 2 meter and sigma Z is like this. As I will put Z1 to Z10, I will get these values. After getting these values, I will draw a plot or will draw a graph. So I am drawing a graph and graph shows the values like this. So sigma Z is decreasing like this. If load is provided here, the sigma Z value will decrease like this. So you should understand this way. Let us move to problem number next. A raft of size 4 meter cross 4 meter carries a load of 200 kilonewton per meter square. So what is raft? Raft is a type of foundation. So raft foundation is given of area 4 meter cross 4 meter, which is carrying a load of 200 kilonewton per meter square. Determine vertical stress increment at a point of 4 meter below the center of loaded area using Boussinesq theory. Again, you are told to find out increment of stress. Let us write given data first. Z is equal to 4 meter, R will be 0. Here raft will look like this. In the figure you can see that here from center every edge is of 2 meter 2 meter. So it is a symmetric kind of foundation. So vertical stress at point P, at this center point P, vertical stress below the center 4 meter, Q is getting 200 kilonewton per meter square. So I am given the load per meter square. So it is loading per rectangular area. So we have to use that concept here. So from question you should get understanding what formulas we should opt. So we have to find out M and N first. So M will be B by Z. So B is 2 and Z will be 4. So M is equal to 0.5. Same way N will be L by Z and N value will be 0.5 again. Putting the formula from there for rectangular loading, I am getting sigma Z dash value as 16.80 kilonewton per meter square. In this formula we have put M, N and Q value only. There is very simple mathematics, but it is too long, so I am not again and again repeating that. So sigma Z dash value, that is 16.80 kilonewton per meter square. Now let us find out vertical stress sigma Z at point P, which is given by sigma Z is equal to 4 into sigma Z dash. Now what is this all? Now sigma Z dash was for only one portion, but actually there are 4 portions, so we have to multiply it with 4. So sigma Z will get 67.20 kilonewton per meter square. So that is how you will calculate in case of raft. Problem number 5. A water tank is supported by a ring foundation having outer diameter of 10 meter and inner diameter of 7.5 meter. So two diameters are given. This ring foundation transmits uniform load intensity of 160. Compute the vertical stress induced at a depth of 4 meter below the center of ring foundation by using Boussinesq and Westergaard's analysis. So we have both the formulas. We have given data, very simple. Q is given as 160, Z is equal to 4 meter, R 0. I am taking it as outer diameter 5 meter and inner diameter is 3.75 meter. We should draw it like that. So red one is inner diameter and blue one is outer diameter. Now I have to put formulas, very simple. Boussinesq analysis, the formulas which we have studied in the previous lectures. I am putting Westergaard's and Boussinesq formulas for circular loading, right? You must remember that. Now value of Q is given as 160, capital R is given as inner and outer. So I have to put the formula in two parts. So I am putting outer diameter here and inner diameter in another formula. So I will get sigma Z by Boussinesq as 23.04 kilonewton per meter square. Let us find out it from Westergaard's formula. Again, it also should be divided in two portions as RO and RI is given. RO is outer and RI is inner diameter. So putting outer diameter first and then we will put inner diameter so that value stays in positive. Sigma Z is coming as 17.57 kilonewton per meter square. Again, Boussinesq and Westergaard will vary. Don't worry about the variation. You just calculate it and put it in the answer. Let us move to problem number next 6. A circular footing 1.5 meter radius transmits a uniform pressure of 100 kilonewton per meter square. Calculate vertical stress at point 3 meter below center. So we have to calculate the stress at 3 meter below. Let us write given data first. So I am given Q is equal to 100 kilonewton per meter square, R is equal to 1.5 meter, that is radius, and Z is equal to given as 3 meter. So here a circular footing is given. So it is a case like this. Circular footing, it will make a cone like this. So 3 meter is its 3 meter is given its depth and 1.5 meter is the radius. 100 kilonewton per meter square is given as loading. Now this formula should be remembered for K. 1 upon 1 plus R by Z square raised to 3 by 2. In the case of circular footings, you should use this. Putting R and Z value as it is given, I am getting K is equal to 0.7159. Now I will use K like this. Sigma Z is equal to K into Q. Now K is multiplied with the loading per area. So I am calculating sigma Z as 71.59 kilonewton per meter square. So in the case of circular footing, you will use these kind of formulas. Let us move to next problem, that is problem number 7. A circular ring type foundation of a water tank. Again a ring type foundation is coming in the picture. Exerts uniformly distributed load of 20. The dimensions of foundations are inner radius as 8 and outer as 10. Determine vertical stress at center of foundation at a depth of 10 and 50. So here two variations are given. First, that is inner radius and outer radius is there, and second 10 meter and 15 meter depth. So we have to put ring foundation formula which we have used in the previous problem but with two changes. So given data is given as small q this, Z is equal to 10 and 15, RO and RI as this. Again this is a case of inner diameter and outer diameter. Let us put the formula as we have discussed. Now here in this formula K, it is divided in two parts as RO and RI is given. So putting RO and RI value, I am getting K as 0.123. Now I have got K value. Now I have to calculate sigma z. So K into Q. So I am getting sigma z as 2.46 kilonewton per meter square. Now I have to do what? For depth 10 meter and 15 meter, I have to find it out that. So till now we have found out for 10 meter. Now let's move to 15 meter depth. Here formula will be same. I am putting z as 15, nothing will change, and I am getting K value as 0.111. So I am finding out stress value 0.111 into Q. That will make it 2.22 kilonewton per meter square. So we should understand that at 10 meter depth vertical stresses are more, but at 15 meter depth vertical stresses are less. So it clearly shows that as the depth increases, stresses will get decreased, like a pressure bulb. So that's it in the numericals part. But before leaving this lecture, you must remember that stress distribution is very much important topic regarding exams as well as different superior level entrance exams. It is very much basic of soil mechanics. It is very much base of soil mechanics. So do prepare well for this chapter as well as numericals. Many exams ask numericals from that and Boussinesq theory as well as Westergaard's theory. Thank you.